Alright guys, so if I have, I'm sorry, I was just going to jump right into this. So we're going to do some practice problems for kinetics for chapter 12. Okay, so, and I'm going to kind of go slow and explain some things to you so you can work this out, but you got to get pretty quick. You don't have a lot of time left, right? You got all of the entire semester to review and this, but I'll as we work through this, I'm going to give you the key items or the points that you need to be thinking about when you're working these problems. Okay, so if I have in this problem, I have problem number 1. The oxidation of ammonia produces nitrogen and water via the reaction below. It's given the reaction. It says if ammonia is being consumed at a rate of 0.72 moles per liter per second, how fast is oxygen being consumed? Okay, so first of all, let's think about some things. Okay, let's think about kinetics, all right, and what's happening. So what is kinetics, right? So it describes the rate of a reaction. And what does that mean? That means that we're talking about the rate at which reactants are being consumed and products are being formed. Okay, so the first thing that you can do is look at this, and you can intuitively kind of rule out any answers that are probably going to be wrong, right? They're just not probable, or they're unreasonable answers. Okay, and so what you can ask yourself is ammonia being consumed faster or slower than oxygen? Well, ammonia is being consumed faster, right? Because for every 4 moles of ammonia, you're reacting 3 moles of oxygen to produce your products, right? So what does that mean? That means that if ammonia is being consumed faster, that means that oxygen is what? It's being consumed slower. And if oxygen is being consumed slower, that means that any answers that are less than what was our time? 72 are our rate. So any answers, you know, that are less than 0.72 moles per liter per second, right? These are possible, okay? They're possibly correct. Okay, and anything that's greater than that, you can just get rid of it. It's not a possibility. Okay. So if the rate of change of O2, all right, is if ammonia is being consumed at this rate, right? And this is the moles per liter per second. That's how we express rate, right? And it's asking us how fast is oxygen being consumed. And so the rate of change of O2, how do we do that? Well, we say, well, the number of moles of O2 per liter per second, right? That's an expression of rate of oxygen, right? Is equal to 0.72 moles of ammonia per liter per second, right? Now what do we want to do? We want to do our mole to mole ratio, right? This is what we're looking for. We're looking at for the rate of oxygen, so we're setting it equal to our given measured quantity, which is the rate of consumption of ammonia, right? So now we want to do our mole to mole ratio. So for every 4 moles of ammonia being consumed, I know that I have 3 moles of O2 being consumed, right? And so these units are going to cancel out, right? And that's going to give me what? It's going to leave me with units of moles of O2 per liters per second. That's the rate. That's what we're looking for. That's what we want. That's what we have left. And when I plug that into the calculator, I'm going to get 0.54 moles per liters per second. Okay? And that's our answer. All right? Now, you know, you can see this if you just look at this intuitively the way I set this up. You know that you could take the ratio of don't know, let's see, you could try 0.72 times 3/4, or you could try 0.72 times 4/3, right? You could try either one of these, okay? Well, if you do this one, you're going to get the 0.54, right? If you do this one, you're going to get 0.96. And you know that this answer is wrong because why? It's got to be less than 0.72 because oxygen's being consumed slower, right? So if you see that and you see the ratios but you're not sure which one it is, just think about it logically, okay? Or just set it up, all right? Okay. So number 2, the rate law for the reaction, and gives us the reaction, has been experimentally determined to be this. Remember, we have to determine this experimentally. We can't just look at a balanced equation and determine the rate law. That didn't happen. Okay, so this is what is the overall order of this reaction? All right, so if I have 1 plus 1 plus 2, what is that? So 1 plus 1 plus 2, that's a fourth order. Fourth order overall reaction, okay? Now, all this is another way to express the rate law, right? And another thing that I could say here is I could say that that this is a first order, right, with respect to bromine, right, because we see that here. I could say it's first order with respect to bromate, right? And I could say that it's a second order with respect to H+, right? So these are just different ways that we could express this, okay? But it asks for the overall, so that's what we had to do. All right. So what are the units of the rate constant for a second order reaction or a third order reaction? Well, first of all, what's the rate constant? Rate constant is K. And what did we say about the units of K when we were going through the lecture, right? We said that the units of the rate constant, they're whatever they need to be, right? They're whatever they need to be in order for rate to equal moles per liter per second. So you don't have to memorize this at all, okay? So this is what is the rate of the units for a second order reaction. Okay, so I know that second order, okay, for second order reaction, the rate is equal to K times what? The square of the concentration of A, okay? So if that's the case, I know that rate has to be what? Moles, and I can write this multiple ways. Remember that. I can write it, moles, I'm going to do it like this, per liters per second. This is what rate has to be. I know that this is concentration, so I know that this is moles per liter squared. So what does K have to be for rate to, when you multiply these two together, for rate to be moles per liters per second? Rate has to be the inverse of moles per liters per second. Okay? Because when I multiply that together, it's going to cancel out one of those moles per liter so that I get what I want. Okay? This is K. All right. Now, what if I did this? What if I ask you this for a third order, right? What if I said I want to know this for a third order? And we know that the rate for a third order is K times the concentration raised to the power of 3. It's cubed, right? Okay. And with respect to A, right? And so we know that if we know that rate has got to be moles per liter per second. And then what do I have here? This is moles per liter cubed, right? So what does rate have to be in this case? You don't have to memorize this. You just have to think about it logically. It has to be moles per liters per second, right, raised to -2 per second, right? So you need to, if you do it like this, then what's going to happen? 2 of these are going to cancel out. It's going to leave you with the moles per liter per second, right? So this is, you could be asked about a 4th order, 5th order, whatever. It doesn't matter. It's not hard, right? This has to be whatever it requires to cancel things out of here to get to this, because it has to have these units. All right, so consider the hypothetical reaction below. So we have A plus B to C plus D. It is found that tripling the initial concentration of A causes the initial reaction rate to be 9 times as great. Okay, so if I take something and I triple it, that means it's, you know, raised to 3, and if I square 3, I'm going to get what? I'm going to get 9, right? So first, I'm going to do a little bit of review down here at the bottom from your notes. Okay, some things that you should know. 0 order is what? Rate is equal to K. And so what does that mean? It means that rate is independent of concentration, right? Okay, if I have a first order, right, rate is equal to the K times the concentration of A. And what does that mean? It means that rate is directly proportional to the concentration of A. And what does that mean? If I double the rate, if I double the concentration, I double the rate. If I triple the concentration, I triple the rate. Okay? Remember that? That's first order. Second order we said that rate is equal to K times the square of the concentration of A, right? So what does that mean? It means that rate is directly proportional to the square of the concentration of A, right? If I had third order, hopefully you're seeing the pattern here, rate would be equal to K times concentration of A cubed, right? So that rate would be directly proportional to the concentration of A cubed, okay? All right. So it is found that the initial concentration of A causes, and so let's just write the general rate formula, where rate is equal to K times the concentration of A raised to the power of M times the concentration of B raised to the power of N. Now this could keep going and going and going, but we're keeping this simple in this class. You guys aren't having to do real difficult kinetics here. Okay, so therefore let's break this down slowly. Okay. All right. So if if we triple the concentration of A, and the reaction rate is 9 times is great, so that means we tripled this and we tripled the rate. I'm sorry, we doubled. Yes, we tripled the rate, and we tripled the concentration of A, right? And what did that do to the reaction rate? It made it 9 times faster. Okay, and so what does that mean? Well, if you take the square of that, 3 squared, it's 9, right? So, and this was for A, right? So this is a what? M is equal to 2. It's a second order. And doubling the concentration of B causes the initial rate to be twice as fast. So that's going to be first order, right? So if we double the rate, because it's directly proportional. This is directly proportional. Rate is directly proportional to the square of the concentration of A, right? And so that's what we saw. We tripled this, right, the concentration, and it causes the rate to be 9 times as fast. 3 raised to the power of 2 is 9, so right, that's why this was second order. This one, in B, we doubled the initial concentration, and the rate was twice as fast. It's directly proportional. If we double the rate, double the concentration, we double the rate. Triple the concentration, triple the rate, right? So this one is first order, okay? So what is the overall order? Well, if rate is equal to K, if the rate of this reaction is A squared times B, well, we don't write the 1, right? But that's 2 plus 1. The overall, this is a third order reaction, right? Because we add the exponents. The overall order is a third order, okay? All right, number 5. The reaction below, we see this reaction, has been found to be a second order. Okay, so that we're getting some information here. It's second order with respect to NO2. So we're saying that it's second order with respect to NO2. What did they just give us? They just gave us the rate, okay? And they said it's zero order, all right, with respect to CO. Okay, so that means if this is zero order, we don't even mess with this guy. We don't put anything down, right? Because what is anything raised to the power of 0? It's 1. So it doesn't matter. All right, so at a certain temperature, the rate constant was found experimentally to be, so we're given K, where we have K is equal to 3.0 times 10 to the negative 5 moles per liter per second, right? Okay, and so, I guess per mole per liter per second. So what is the rate of formation of CO2 at this temperature when the concentration of NO2, so it's telling us that the concentration of NO2 is equal to 6.4 moles per liter, okay? And that of CO, we don't care what CO is, right, because it's zero order. And that of NO, it's 5.2 moles per liter, and that of CO2, it's 1.3 moles per liter. Okay. So there's some things we need to think about. First of all, it's relating everything, right? So rate depends on what the coefficients are. Okay, and so when we're asked about this rate of formation, and we're asked about and we're given all this information where we're actually asked to relate the products, the reactants and products, right? We need to think about the reciprocal. So if we go back up here to the first, this first reaction right here, right? And if I were to relate each of the rates to you of the reactants and the products here, right, then I would say, okay, if I were to ask you about the rate of this, so I would say the rate is equal to, if I had to relate each one of these, negative, I'm going to take the reciprocal of the coefficient, negative 1/4, right, the change in NH3 over the change in time is equal to negative 1/3, because I'm taking the reciprocal of the coefficient, right, of the change in O2 over the change in time, which is equal to 1/2 the change, oh, I'm sorry, these are supposed to be the concentrations. Oh, I'm messing up there. The concentration of N2 over the change in time, plus, what is this, 1/6 the change of the concentration of water over the change in time. Now, remember, the reactants are being consumed, so we don't view rate in a negative form. So we always put this negative number to ultimately get rid of the negative, right? Because we want rate expressed in a positive. So anytime you see reactants, you think about them being consumed, so they're disappearing. They're being consumed, they're disappearing, so they have a negative value. Okay. So we have this idea here, except, you know, I'm just telling you this because in this particular reaction, it's a 1-to-1 ratio here, okay? So we don't have to take reciprocals of anything. But if we didn't have 1-to-1, we would, okay? And so if we relate these, right, to where I say, okay, the rate is equal to the negative the change in concentration of NO2 over the change in time, plus the negative change in concentration of CO over the change in time, right? I'm sorry, this is not plus. We're equating this. This is just equal. Sorry about that. Okay, these are reactants, so they're negatives. Now we're talking about the formation, the products here, so we're not going to do negative, right? It's positive. And then we just have the change in concentration of NO over the change in time, which is equal to the change in concentration of CO2 over the change in time. Okay, so what do we have going here? We've got the rate of consumption, right, and the rate of formation. Okay, so these are always going to have negative signs, and these will be positive. Okay, all right. So, and remember, this is just due to the disappearance of the reactants because they're being consumed. Okay, so now if we think about the rate of formation, okay, we only really need to be concerned with the concentration of NO2 because the rest of these, they were zero order, okay? And so, because what we were told is that we have a second order with respect to NO2 and a zero order with respect to CO. So we don't care about CO, we only care about CO2. So if we know that the rate of this reaction is equal to K times the concentration of NO2 squared, then we can say that the rate is equal to, we were given K, that's 3.0 times 10 to the negative 5, right? Go ahead and put the units in here, times, what were we given? The concentration of this is 6.4, right, moles per liter, which we know that to be molarity, sorry about that, right? And this is squared because it's second order, right? That's going to be equal to 1.2 times 10 to the negative 3 moles per liter per second, right? And this is the rate, this rate right here is not just the rate of consumption of NO2, it's all a 1-to-1 ratio. This is the rate for the consumption and formation for every single one of these. They all disappear and they all form at the same rate, okay, because they're 1-to-1 ratio. All right. All right, so let's consider this number 6. Consider the hypothetical reaction of A plus B plus C forms these products. The following initial concentration and initial rates were obtained for the reaction at 25 degrees C. What is the correct rate law for this reaction? Okay, well, there's some things that we can look at here to see if we can determine this by inspection. Okay, so the first thing that we need to look at, because we've got three different concentrations here. So what do we know? We know that rate is equal to, we're just going to do the general formula, K times M, A raised to the concentration of A raised to the power of N, concentration of B raised to the power of N, and the concentration of C raised to the power of P. We don't put O because it's hard to tell between O and 0, right? We don't want to do that. All right. So, okay, I'm just going to look at some things and see what I can do here. Now, technically, we could probably do all these by inspection, but I'm going to show you how to do some of them in case you've forgotten when you can't do it necessarily by inspection. All right, so if I say this is reaction 1, 2, 3, and 4, okay? Remember, anytime I compare these, I want to divide with the big number on top. So I'm just going to compare reactions 1 and 2. And I'm going to do that because what I noticed between 1 and 2 is A and B are held constant. C is the only one that changed. C doubles and the rate changed. Okay. Now because this is a 10 to the negative 2, all right, this is a bigger number than 10 to the negative 3. 0.6 is a bigger number than 0.3. So I'm gonna write this first comparison where I look at reaction 1 and 2. Okay, I'm gonna put 2 on top where this is number 2 and this one's number 1, and I'm gonna start with the rate because we're doing rate here, right? And so I have rate is equal to, for number 2, I've got 1.68 times 10 to the negative 2. Number 1 is 4.20 times 10 to the negative 3. This is equal to, I've got K, all right, times, here we go, initial concentration of A is for reaction 2 is 0.100, right, raised to M. B is 0.200 raised to N. And C is 0.600 raised to P. Okay. Now I'm going to look at reaction 1. Reaction 1 is K, right, because I'm just following this. That's all I'm doing, right, and I'm just filling in. So I've got 0.100 raised to the power of M times 0.200 raised to the power of N, right, because we're taking these here. And then I've got 0.300 raised to the power of P. Now I can start canceling some things out, right? These are all the same. And so this is the only thing that's different, okay? And so when I look at this, when I divide this out, I'm going to get 4 is equal to 2P, right? Therefore, P is equal to 2. So this guy here is this second order, right? Okay. So that's that one. Now so we've looked at 1 and 2. So now let's see. If I look here, what happens here? If I look at 1 and 3, right? A stays the same. C stays the same, B doubles, but the rate doesn't change. So what I'm going to do on that one, because we can do this one by inspection, we don't need to do anything else with it. There's no need to multiply or divide or whatever. Okay. So if I look at that, at number 1 and 3, right? What's that? If concentration, if doubling the concentration has no effect on the rate, I doubled the concentration and the rate stayed the same, what order is that? It's 0, right? And where did we keep things constant? In A and C, but where did we double the concentration? B. So the order with respect to B is 0. Okay? All right. So now let's look at what else do we have that stays constant? Let's see. If I look at 1 and 4, 0.3 stay constant, 0.3 stays constant, 0.2, 0.2, and what changes? The concentration of A, right? So here I've tripled A, and I've got a change in my rate. So let's look and see what's going on there. Okay. So now I'm going to compare reactions 1 and 4. But look, 1.26 times 10 to the negative 2. That's a bigger number than this one. Okay. So we're going to divide by the bigger number, right? So I'm going to do number 4 over number 1. So that I've got 1.2, I should have done that there. 1.26 times 10 to the negative 2 over 4.20 times 10 to the negative 3, right? Now, hopefully what you've noticed here is we really don't need to write this constant stuff down, right? We only really need to write down what actually changed. Now, if you don't understand that, you don't understand this shortcut I'm about to do, then don't do it. You do it the long way, okay? But I'm not going to write down, so what actually changed? This one did. But if I look at B, the concentration in reaction 1 and reaction 4, they stayed the same, right? In concentration of C, they stayed the same when I'm comparing these two. What changed? The rate. So I'm only going to write down the variables that changed. Okay, so I've got this, and so I'm going to put number, again, it's 4 over 1, so I'm going to say I've got, and I'm not going to even write this K, because I know the K's are going to cancel out as well, right? So I'm only going to do 0.300 divided by 0.100, okay, raised to the power of what? M. All right? All right, and so when I do this, I'm going to get 3 is equal to 3m, right? Therefore, m is equal to 1, okay? And so this guy is first order with respect to m, okay? Now, we typically don't write down zero order. We leave them out, right? If it's first order, we don't write the exponent. So what is the rate for this guy? So the overall rate here is if the actual rate law is rate is equal to K times the concentration of A times the concentration of C raised to the power of 2. Okay, so all right, this is the rate law. That's your answer. Okay. Number 7, consider this first order reaction. Okay, so we're told some things that we need to pay attention to. This is a first order reaction, okay? And then what do we want to know? We want to know the half-life of this reaction, okay? Now I'm going to tell you right now, a mistake a lot of students are going to make is they're going to think they can do something by inspection on this, and they're going to be wrong. Because I'll tell you what the first answer is going to be on here. There'll definitely be an answer of 72 seconds. And why is that? Well, because you're going to look at this and you're going to say, okay, if a quarter of the reaction disappears in 36 seconds, then half of the reaction should disappear in 72 seconds. And that would be wrong. Because this is not a linear relationship. It's not a straight line. You can't think of it that way. Okay, so don't get tempted to do that. Okay? Anytime you're talking about half-life like this, we're talking about time. We've got seconds in here. There's time. What do we have to do when time is involved? We have to use the integrated rate laws. Okay? This is a first order reaction. This is not a zero order reaction that gives you a straight line relationship. This is a first order reaction. Remember that? You go back in your notes, your first and second orders, even the zero order, they all have an integrated rate law for time. Okay? All right. So, let's look at this. So here's some key points. All right, so number 1, if we can use, because this is first order, the natural log, that's just an n, sorry, of the concentration of A at time t over the initial concentration, and remember this is, we have to log the whole, take the natural log of the whole quantity, is equal to negative K times t. Okay? We're going to do this, okay, we use this, okay, to determine K. That's the point of this first step. The second step, okay, is we're going to use the half-life, T1 half, okay, for our first order, T1 half is equal to the natural log of 2 over K. Okay. All right. And that is to find the half-life. All right. So let's look at that. Now, let me ask you something. What does this mean? Right? What is the ratio of the concentration of A at time t over the concentration of A, initial concentration? Remember, this is real important. This is key to this problem. It's the fraction of A remaining at time t. Okay? This, you have to understand this, right? Because this is what sorry, I didn't mean to put, let me get rid of that. There we go. All right. So here's our, you got to understand this. It's important. Okay. All right. So now, if 25% of A has disappeared, how much remains? What's the fraction remaining? It's 0.75, right? So that our first step here is we're going to say the natural log of what? 0.75, okay, is equal to negative k times 36 seconds, because we were given the 36 seconds, right? We were given what this is 0. We were given what this is, right? Well, we had to determine it, but I mean, it wasn't hard, right? And so therefore k is equal to 0.00799 inverse seconds, okay? Number 2, we're going to plug in here. If the half-life of a first order reaction is equal to the natural log of 2 over k, then that means, remember, if we punch in the natural log of 2, that's just 0.693 over what was k, 0.00799, right? So what does that give us when we work this out? It means the half-life here is equal to 87 seconds, okay? And this is our answer. But this is key. If you can't do this, you're going to be stuck because you're not going to know what to take the natural log of, okay? All right, number 8. So a chemical reaction that is first order in Na is observed to have a rate constant of whatever. So this is K, right? They're telling us what K is again. And the initial concentration of A is this. So this is, A naught. What is the concentration of A after 200 seconds? Okay, and we're also told what? This is a first order reaction. So we're given quite a bit of information, all right? Okay, now, again, just like we did a minute ago, right, we want to use the natural log of the concentration of A at time t over the initial concentration of A. Remember, you got to take the natural log of the whole quantity, which is equal to negative k t. And what was this again? This was our ratio, our fraction of time, right? And then the second thing we're going to do is we're going to use the integrated rate law, first order integrated rate law. I'm going to write it a little bit different. If we use our the properties of the logarithms, I can rewrite this as the natural log of the concentration of A at time t is equal to negative k t plus the natural log of the initial concentration of A. Okay, we can do that. All right, and remember, this forms the equation of the line, right? Y equals mx plus b. Okay. And so in this problem, here's the thing. We know what K is, right? We know what the initial concentration of A is, right? And we have a time, right? So which equation of this is going to be the easier one to work with? It's going to be the second one, right? So we can just say that the natural log of the concentration of A at time t is equal to negative, what was K? It was 1.2 times 10 to the negative 2, right? And as long as your units are right, you don't have to worry about canceling all that stuff out, but you have to know what your SI units are supposed to be. We're going to multiply that times 200 seconds, okay, plus the natural log of 2, right? And when we plug that into the calculator, we're going to get negative 1.707. Now, that's not our answer, okay? That's not our answer, because what do we want to know? This gives us what? This gives us the natural log of the concentration of A at time t is equal to what? Negative 1.707. Now, let me ask you something. How do we get the concentration of A out of here? Well, if you look on your calculator, all right, you've got a button there that has the natural log of x, and right above it there is an e raised to the power of x, okay? This function here, e to the power raised to the power of x, this is the inverse of the natural log of x, okay? And so you need to make sure that you practice this. So if you plug that in other words, we can say, therefore, that the concentration of A at time t is equal to e raised to the power of negative 1.707, okay? If we punch that into our calculator, it's going to equal 0.18 moles per liter, okay, which equals the concentration of A at time t. All right, and this is our answer. Okay, and that's how you would do that. You got to understand your logarithms, okay, and the properties, and in these rate laws. You're going to be given all these rate laws, right? But you're not going to be told which one is first order, second order, zero order. You've got to practice this. If you guys don't practice, you're not going to be able to get this stuff right, okay? All right, so let's move on to this one. Okay, so the decomposition of ethylene oxide, all right, we're given that reaction. It says in a first order, okay, we're given something important, with a half-life. Nope, look at that. We're given time. How long? You know, if you're asked about time, you're going to have to use an integrated rate law, because the integrated rate laws, they're the only ones that have time that's not hidden in the denominator somewhere, right? You can actually solve for time. And so it says, how long will it take for 90% of the sample of ethylene oxide to decompose? First thing you should do, if you see this, you've got 90%. What's the fraction remaining that's not reacted here? It's 0.10, right? That's not reacted, okay? Or we could say remaining. All right? Okay, so you've got to pay attention to those things. So the first thing we're going to do is say, all right, I'm asked here, how long will this take? Now, look, in this last problem, where'd it go? All right. This right here, no, it wasn't this one. Where did it go? 170, 171. Yes, it was. Okay, you see how this is expressed here? That didn't mean anything to anybody, right? Nobody likes that, right? Well, chemists don't. I can tell you that. So what we're looking for, we prefer things written out in half-lives. Okay, we like to, because the half-life makes a lot more sense. So there's two steps to this. Okay. One is, we know, again, we're dealing with the first order. So number one is we're going to use the definition, okay, DEF, the definition of half-life, which is expressed as T sub 1/2 is equal to the natural log of 2 over K. This is the definition of the half-life for a first order reaction, okay? And now we're going to use number two, okay? We're going to use the first order integrated rate law, all right, to find the time, to find T, okay? And so what are we going to do with this one? What is this reaction? So I'm just going to kind of draw a thing up here so I don't have a lot of room here. It's the natural log of the concentration of A at time t over the initial concentration of A is equal to negative KT. Okay? Alright, that's what we're going to use these two. Okay, so number one, T 1/2, the half-life here, is equal to the natural log of 2 over K. I'm going to rearrange because I wasn't given K. I've got to find K. Right? So that K is equal to the natural log of 2 over T sub 1/2. Okay? So that is going to be 0.693 divided by We were given this halftime of 56.3 minutes, and that's equal to 0.0123 inverse minutes. See, that, I mean, you know, the 56.3, a half-life, it just makes so much more sense to people than the rate constant, right? This inverse minutes. I mean, what is that? All right. So number 2. Now we're going to use the integrated rate law, and we're going to take the natural log of the concentration of A at time t over the concentration of A, the initial concentration of A, is equal to negative kt. Okay. Now look, we just have to solve for time here, but we know what the log is that we're going to take. What is this ratio? It's the fraction not reacted. We told 90% did react, or how long it will take for this to react. That means that 0.10 didn't react, right? So therefore, we can say that the natural log of 0.100 is equal to, we were given k, or we weren't given k, we solved for k, and we said it's 0.0123, right, inverse minutes, okay, times t. Okay, that's easy enough to solve for, right? And so t, we solve for t, we're going to get 187 minutes. All right, that's our answer. Okay. All right, number 10. Cyclopropane decomposes to propane at 450 degrees C. The decomposition is first order with a rate constant. So again, we're given K. What is the half-life? It wants to know T sub 1/2 is equal to what of cyclopropane. Okay. Now, what were we told? First order. What's the half-life that we use for first order? T sub 1/2 is equal to what? The natural log of 2 over K. We were given K. Now, you're probably not going to get anything this easy, but I'm just trying to help you work some problems to see, you know, how you could rearrange this. You can find a half-life, you can find K. It just depends on what you're given. This is just simple plate and chug, right? And you need to know, anytime you're asked about the half-life and it's a first order reaction, you've got two equations you've got to work with. You've got this one and this one. Okay, and you need to know your log properties in order to rearrange this if you need to make it easier to work with. All right, but you got to know these. Okay, all right, and so I mean you can obviously they're going to be on your useful information page, but you have to know that these are associated with the first order. It's not going to do you any good to not look at these integrated rate laws and not know what order they're with, or you're going to be lost. Okay, all right, so this is equal to 0.693 divided by what was K, 0.560, right? Inverse minutes is equal to 12.4 minutes. Okay, so that's the half-life. You can't get any easier than that. Okay. All right, so the thermal decomposition of N2O5 proceeds as follows. And you're given a reaction. And it says this is a first order reaction with a rate constant. You're given K. You're told it's first order. How long would it take to take 20% of this to decompose? Okay, so if 20% are going to react, what does it leave me? It means that remaining, it's the first thing you should think about. Remaining is what? 0.80, right? Okay, and so again, this is first order. I'm going to take the natural log of the concentration of A at time t over the initial concentration. Got to take the natural log of the whole thing, is equal to negative K times t. Okay, this is the fraction remaining. So what am I going to do? I'm going to take the natural log of 0.800, which is equal to negative 5.10 times 10 to the negative 4, right, times t, and again you rearrange for time, and that's 438 seconds, and that's our answer. Okay, these are just simple plug and chug problems if you understand what you're doing. Okay? If it asks how long, you got to use an integrated rate law, and you have to use it for the proper order. Right here it's first order, so this works. Okay? Alright, so consider the reaction of A to products. If I plot 1 over the concentration of A versus time in a straight line, what can be said about this reaction? Now, if you already know these plots, you're good to go. You already know what this is, okay? But if you don't, well, you might be in trouble. So let's do a little bit of review. If I know that for a first order reaction, that my integrated rate law is the natural log of the concentration of A at time t is equal to the negative K times T plus the natural log of the concentration of the initial concentration of A. This is my first order integrated rate law. My second order integrated rate law is 1 over the concentration of A at times T is equal to K times T plus 1 over the initial concentration of A. And my zero order, okay, is the concentration of A at time T, which is equal to negative K times T plus the initial concentration of A. Okay, so these are our integrated rate laws for first, second, and zero order. So if I were to plot the natural log of the concentration of A versus time, what do I get? Okay, in order for me to get a straight line, this is what I have to do. So if I plot the natural log of the concentration of A versus time, I'm going to get a straight line. Okay, if we have the plot of 1 over the concentration of A versus time, we're going to get a straight line. If we plot for zero order, okay, this is for first order, second order, zero order, the concentration of A versus time, I'm going to get my straight line. Okay? So, having reviewed this information, if the plot of 1 over the concentration of A versus time is a straight line, what can be said about this? What is it? It's a second order reaction, and you should know this without having to review or look at anything. Okay? Alright, so that concludes the, I think that concludes the problems, yeah, for Chapter 12. So that wraps us up. Guys, please, please, please do these and do your end of chapter problems. I promise you, it will help you considerably on the final. You'll be prepared. If you can understand the problems in the problem session and your end of chapter problems for chapters 11 and 12, you will do just fine on the final exam. Okay? All right, well, that's all I've got for you, and I hope you have a wonderful study time for all your classes and that you do excellent on your finals.